Behind this wall of concrete sits millions of tons of water, every second, every minute, every year. It's pushing against the dam with enormous force. The pressure never switches off. The dam never gets a break. Yet some dams have stood for more than a century without failing. So how does a wall of concrete survive one of the most relentless forces on Earth? And what stops all that water from simply winning? Water looks calm, but appearances are deceptive. The deeper you go, the greater the pressure. Near the surface, the force is relatively small. Near the bottom, it's immense. That pressure is constantly trying to do two things: slide the dam downstream or rotate it until it tips over. Engineers call these sliding and overturning. Two failure modes every dam must be designed to resist. But there's another force, one you can't see, one that doesn't push on the front of the dam at all. It attacks from underneath. Water slowly seeps beneath the foundation, creating upward pressure that quietly works against the dam's own weight. This is called uplift. And for decades, it was one of engineering's greatest hidden threats. The simplest solution is also the most powerful. Make the dam so heavy, the water simply can't move it. These are called gravity dams. They don't rely on cables or anchors. Their own weight keeps them standing. That's why they have their distinctive shape. Wide at the bottom, narrow at the top. Every extra ton of concrete is placed exactly where it's needed most, where the water pressure is greatest. It's not architecture. It's physics. Take the Hoover Dam. Its enormous mass holds it firmly in place, resisting the water's push with sheer weight and stability, the same way a heavy enough object simply won't budge no matter how hard you shove it. But engineers eventually discovered there was an even smarter way, one that uses geometry instead of sheer weight. Instead of fighting the water head-on, an arch dam redirects it. Its curved shape channels the force sideways into the surrounding rock. The canyon walls become part of the structure itself. It's the same principle that's allowed stone arches to survive for thousands of years: compression. Instead of resisting the load directly, the dam spreads it into the mountains. The result? Far less concrete, far less weight, but there's a catch. Without incredibly strong rock on both sides, an arch dam simply won't work. Even the strongest dam can fail if engineers underestimate what lies beneath it. In 1928, California's St. Francis Dam collapsed. Within minutes, a wall of water swept through the valley below. More than 400 people lost their lives. Investigators later concluded that uplift pressure beneath the foundation had played a major role. The water wasn't destroying the dam from the front. It was weakening the very force keeping it in place. It became one of the most important lessons in dam engineering. Today, modern dams include drainage galleries, relief wells, monitoring instruments, and drainage systems specifically designed to relieve that hidden pressure long before it becomes dangerous. But water isn't the only thing engineers prepare for. Imagine holding back a reservoir the size of a small lake. Then suddenly, the ground begins to shake. An earthquake doesn't just move the dam, it moves millions of tons of water. As the reservoir surges, it creates a sudden spike in pressure against the structure. Engineers call this hydrodynamic pressure. It's a force that only exists during an earthquake. But when it appears, it can be enormous. That's why dams in seismic regions are designed for specific earthquake loads, often with significant safety margins beyond expected events. It's protection built for a disaster engineer's hope never arrives. From the outside, a dam appears completely still. But every second, it's resisting water pressure, countering uplift beneath its foundations, preparing for earthquakes that may never happen. It's fighting an invisible battle around the clock, A dam doesn't survive because concrete is strong. It survives because every force acting on it has already been calculated, balanced, and accounted for. Thousands of engineering decisions, working together, without stopping, for decades, sometimes centuries. And that's what lies beyond concrete.
If you enjoyed seeing how engineering makes structures like this possible, subscribe to Beyond Concrete.